substitution rule, and this is probably the most important or the most used rule when you're taking antiderivatives or indefinite integrals or definite integrals. And it's basically substitution going backwards. Okay, so what you do is you look at like a function that's a composition of two functions. And so f of g of x, okay? You're looking at that. And the g of x, this is the inner function, and the f is the outer function. So you let u be the inner function. And now this choice is kind of sometimes can be hard to make, but if you just need a lot of experience to be able to figure out which the best choice, in my opinion. So you choose, you let, okay, so here's the deal. You have an integral like this that you want to do. You let u be the inner function. Okay, and what happens is you need to have like the derivative of the of this inner function, g prime of x, being multiplied by f of g of x. You need to account for all that. And if you have that, and if you make the substitution, then this integral becomes the integral of f of u du. Okay, so I guess it's best to just show you with an example. So I've got number 1 right here. And here you have x squared times the square root of this. So now this right here, this x cubed plus 31, is inside of the square root. So this is the inner function of this composition of the square root and this x cubed plus 31. X cubed plus 31 is the inner function. So you let u be that, okay? Now, after you do that, what you want to do is calculate du. Or du would be the derivative of this with respect to x. So that's going to be 3x squared dx. Okay, so you calculate that. Now, what you notice is you have an x squared here, and you have a dx, right? Which is all this. But you don't have the 3. So what I do have, I'm going to solve for what I actually do have on this integral, which is x squared dx, and make that du over 3. Okay, now I do all my substitutions, and what happens is this x squared dx turns into du over 3. I'm going to put that on the end. This square root, I'm going to rewrite that as raised to the 1/2. And x cubed plus 31 is u, so that's going to be just a u. Okay, so essentially I have the integral of u to the 1/2. I'll take the 1/3 all the way out, du, like that. Okay, so now I integrate this, and this is just a monomial. So this 3/2 gets raised up. I mean, 1/2 plus 1 is 3/2. So it's u to the 3/2, but then I'll need a 2 and a 3 to counteract that, in addition to this 1/3 that's already there. And then I have my constant. And so this is 2u to the 3/2 over 9 plus a constant. Okay, now you need to switch it back in terms of x's. So this u is x cubed plus 31. So I'm going to put x cubed, right, a better 3 there, x cubed plus 31 to the 3/2 over 9 plus a constant. And there you go. That's how you do it. That's how that works. Okay, so let me give you more examples. And then you can verify this. So the idea is this: if you take the derivative of this, then what will happen is it's going to be the power chain rule. So this 3/2 is going to come down. It's going to knock the 2 out, and one of these 3's it's knocked out by that. Then this reduces by 1 power to 1/2, which is basically the square root of x cubed plus 31. And then you multiply by 3x squared, so 3x squared comes out. The 3 takes this other, reduces this all the way down to just a 1. And then you have an x squared, which is right there. So if you take the derivative of this, you're just going to get that. And that's, of course, that's another way to do it. And I would recommend, doing it that way as well. Instead of going through all this process of letting u be this and du and then du over, and then solving for that part, you can also just look at this and say, oh, well, this is this. Because if I take the derivative of this, then I'm just going to get that. So that's perfectly fine to do it that way as well. Okay, let's go on. So all of the problems from this section are dealing with this. And so the idea is, well, one of the biggest parts is trying to figure out what you should let u be. And in this case, I'm going to let u be equal to 4x plus 9. So it's just what's right there. So it's just the denominator here, 4x plus 9. So that means du would be, I'm going to take the derivative of this. The derivative, that's 4, and the derivative, that's 0. So then I just put a dx on the end. Okay, so 4 dx. And so that means that dx would be du over 4. So this dx gets replaced with du over 4. So that dx got replaced with du over 4. And this piece right here, this 4x plus 9, gets replaced with the u. Okay. So this 4x plus 9 gets replaced with the u because of this right here. Okay. So then I can pull that 1/4 all the way out, and I have du over u. And of course, the integral of that is the natural log of the absolute value of u plus a constant. And then the last step is you substitute this back in. So 4x plus 9 right there. Okay. So because u is 4x plus 9, then you substitute u back right there. And that's it. That's it. That's all. That's the answer. Okay. Okay, let's do number 3. So here, the best thing is to let u be log x, because it's the inner function. So you have this log x, it's raised to the 40th power, right? So the log x, and then I can go du will be the derivative of log x is 1 over x dx. And you notice that this is the same as that. So this one, we don't even need to like solve for this because it's already right there. There's not like a constant or something dividing it or nothing like that. So this becomes, okay, so we replace this log x with a u, so that's u to the 40th. And then this dx over x is just du, like that. And then, of course, you can take the antiderivative of that, which would be u to the 41. Okay, so when you take the derivative of this, you get a 41 coming out. So we'll cancel that off with the 41 down here. And then this reduces by 1 to give you 40, plus a constant. And then the final step is you substitute this log x back in for the u. And you get that. Okay, let's look at the next one. Here you have the square root of something, and so that something is the inside. So that's a good choice for your u. 9 plus e to the x of your u. And our du becomes the derivative of that's 0, the derivative of this is just e to the x, and then tack a dx right there. And then you'll see that this is the same as both of these terms there. And of course, this inside part is u. So we have u to the 1/2 du. Just comes down to that, and it's not too bad. So you raise that by 1 power. When you take the derivative, you have a 3/2 coming out. So we'll put a 2/3 there to counter that, plus a constant. And finally, substitute the 9 plus e to the x back in. So this u gets replaced with 9 plus e to the x. And there you go. Okay. So number 5. Here, again, you look for the inner function, and it looks like this cotangent x is inside this. So we'll let u be cotangent of x. And the derivative of cotangent is negative cosecant squared of x. And so you have a cosecant squared x dx. You've got this part right here, which is right there, but you don't have this negative sign there. So we'll just take that to the side. And when we do our substitution, then it becomes negative du. So there'll be a negative there. So the negative comes from here. And then put the u into here. This is the 8th root of cotangent x, 8th root of u, or u to the 1/8. Okay, so we can take the antiderivative of that. You just raise that by 1 power to the 9/8. So 1/8 plus 1 is 1/8 plus 8/8, which is 9/8. And then when you take the derivative, you have a 9/8 coming out. So I'll put 8 to 9 to counter that. And then you substitute back. So cotangent x goes back in for you. Probably should use I think Webassign might want you to use this right here. Okay, and that's all over 9 plus constant. Okay, let's go on to the next one. Okay, sometimes it's kind of hard to figure out what to do, what to choose or u. That's going to be probably the hardest part, trying to figure out what you should make your u. And a lot of times it's pretty difficult. So you might, so like if you approach this problem right here, you might think, well, if I make the u equal to 1 plus x to the 20th, then that would be good. But it turns out that that really doesn't work too well, because if you take the derivative, so this would be wrong to do this, to let u equals 1 plus x to the 20th, because then your du would be 20x to the 19th. And there's no x to the 19th in here at all. There's an x to the 9th, but there's no x to the 19th. So that's not going to work. Whoa, it just disappeared too. So that's not going to work. But what you can do, so sometimes there's little hints here. And one of the hints is that you have this x to the 9th, right? So if you take the integral of x to the 9th, you get x to the 10th, or 1/10 x to the 10th. So if we make u equal to x to the 10th, and you kind of have to think a few moves ahead, but let me just show you what happens if you make u equal to x to the 10th. So then du becomes 10x to the 9th dx. And here, the nice thing is that this x to the 9th dx is right there. Okay, so that will be handled by that. So that's good. So we'll go ahead and solve for that. X to the 9th dx. That would be 1/10 du. Okay. And so if I make all the substitutions, then I have, so this x to the 9th dx becomes 1/10 du. So I'll put the 1/10 there, and I'll put a du on the end there. And then this inside part, that becomes 1 plus, okay, so if u is x to the 10th, then this is u squared. And now, you know, if you could see this from the beginning, that would be great. But if not, that's fine. But now you can kind of see that, oh yeah, you recognize that this is the antiderivative of this is the inverse tangent. Okay, so that's going to be the inverse tangent of u plus a constant. Okay, so you see that right there. Okay. Okay, so now you go ahead and you substitute back. Oh, that was wrong. You substitute the u back, and so you have inverse tangent of x to the 10th plus a constant, and that will be the answer right there. Okay. So again, the biggest trick is going to be trying to figure out what this u should be. And when you have that, when you choose u, I'll just say one thing right here. When you're choosing the u, you have to account for everything. It has to wipe out everything. You can't have any extra x's left over anywhere. They all have to be eliminated. This, you have to turn, you can't have any x's in this at all. If you do, then there's no way you can integrate this. Okay, you have to get rid of all the x's, transfer them in terms of u or whatever, and then hopefully it can be integrated. But yeah. Okay, let's look at number 7. This is a little bit more tricksy because if you let u be, so the first obvious choice would be to let it be x squared plus 39. But then, okay, and then you go du, the derivative, so you take the derivative of that, that's 2x dx. And, but you have an x cubed here. And so that is a problem to deal with. But you can get around that because, by doing this, and this is kind of tricky. Let's split that up into an x squared times x. Okay, so now I'm going to split that up into an x squared times x. So x cubed is x squared times x. Now this one right here, this one right here, this x dx on that is exactly this part right here. Okay. And so let's see, x dx will be equal to du over 2. Now this x squared is kind of interesting, and that one you can actually, if you subtract 39 from both sides, you get that. Okay, so what I'm going to do is I'm going to plug that in for that. I'm going to plug in this for that, and we're going to plug in this for that. Okay, so everything, all these x's are getting replaced with an expression in u. Okay, so the x squared is u minus 39. The x squared plus 39 is u, so u to the 1/2. And then the x dx is du over 2. I'll pull the 1/2 out all the way over there, like that. Okay, now, if I'll leave the 1/2 out here. Okay, so now let's distribute the u to the 1/2 in. So that's going to be u to the 3/2. So u times u to the 1/2 is u to the 3/2 minus 39 u to the 1/2 du, like that. Now I can integrate. So I raised that by, I add 1 to 3/2, that's 5/2, and then I need a 2/5 to take care of that. And then I raised this by 1 to 3/2. So 1/2 plus 1 is 3/2. But then I'll need a 2/3 to counter that. And then I have plus a constant. And interestingly, there's a 2 here and this 1/2. So those are gonna all cancel out. When I distribute this 1/2 in, it's gonna knock out all those 2 terms. And so I have u to the 5/2 over 5 minus 39 u to the 3/2 over 3. So then I replace the u with x squared plus 39. So I've got x squared plus 39 to the 5/2 over 5 minus 39 x squared plus 39 to the 5/2 over 3 plus a constant. And there you go. So that's the integral right there. Okay, so let's go on to more problems. Okay, now what we're getting right here is how to evaluate definite integrals. So here, the difference is we have limits on here. Okay, now if you go back to the first page, then pretty much all of this is the same as this right here, you know, with that. And the limits, instead of going from a to b, you're going from g of a to g of b. Okay, now when I do this, I like to do this, and like this is kind of like, whoa, why is it doing that? But I'll show you why that's the case. Why you change the limits like that. Now you could also, if you want to, there's basically 2 options here. You could like make this substitution all the way, or you could just like treat it like an indefinite integral, you know, and find an antiderivative right down to here, and then just tack the original limits onto this one, because this is an x. This final answer is an x, right? Just tack the limits onto that one. Okay, so there's 2 ways you can go with this. Okay, let me show you the way that their formula on the first page is suggesting. Okay, so first of all, we have to figure out what the u is. So in this case, we can let u be cosine t. Okay, and then du is going to be negative sine t dt. And so you'll notice that you've got this sine t dt, and here you have a sine t dt. Okay, so that's gonna, this is gonna get replaced with, bring the negatives over to the other side. Okay, so all of that right there is gonna get replaced with a negative du. Okay, and so we can go ahead, let's go ahead and write this. So this part right here gets replaced with a negative du. And then you have cosine squared. U is cosine, and so this cosine squared gets replaced with u squared. Okay, so that's handling all this, just like we previously did with this value for u. And then this one can be integrated. Now the limits. These limits are in t. Okay, that's t equals pi over 6 and t equals 0. Those are the limits from 0 to pi over 6, 0 and that. This integral is in u. We know that u is cosine t. So if t is pi over 6, then u would be cosine of pi over 6, okay? Because you want to have these in u, which is, let's see, what's cosine pi over 6? Let's see, pi over 6 would be view 1, 2, root 3. So cosine is be root 3 over 2. Okay, so this upper limit is going to be root 3 over 2. T equals 0 corresponds to u equals cosine of 0. Okay, so if t is 0, then u is cosine 0, which is 1. Okay, so you're going from 1 to root 3 over 2. Now what's interesting is a lot of times when you do this, see here you have a smaller number, 0 going to a larger number, pi over 6. Here you have root 3 over 2 is actually smaller than 1. So you have a larger number going down to a smaller number, and that's perfectly fine. That's perfectly fine for that to happen. If you really want to, I guess part of it is this negative sign right here. You could but we'll just leave it alone though, okay? You could reverse the order and then just get rid of this negative sign. That would be the same. Okay, I'm going to rewrite this as u to the minus 2. That. Okay, now we'll take the antiderivative of u to the negative 2, which is u to the negative 1, or negative u to the negative 1. So if you think about it, if you take the derivative of this, you reduce this by 1 power to a negative 2. So negative 1 minus 1 is negative 2. You'll pull the negative 1 down, which, okay, there's a negative right there, so great. That just handled it right there. So that's it. So from 1 to root 3 over 2. Okay, so now you put in the upper limit, which is, I can also write this as 1 over u. Then I put the upper limit in, which is going to give you 2 over root 3 minus 1. And that's it. Okay, let's go to the bottom one. So you have e to the 1 over x squared dx. And what I'm going to do is I'm going to let u be 1 over x, which is x to the minus 1, because that's the inner function on this e part, right? So du will be, okay, you take the derivative of that, that's going to have a negative come down and be x to the negative 2. Okay, which is the same as negative 1 over x squared. Oh wait, I forgot the dx. And so you'll notice that that is the same as all that. So that's going to wipe all that out. But you'll have to replace it with a negative. So pull the negative over here and do that. So there'll be a negative from here. And then this e to the 1 over x will be e to the u. Okay, so all that part got replaced with e to the u du. Now, the limits are x equals 8 and x equals 1. So u is 1 over 8. And here u is 1 over 1, which is going to be 1. So you're going to go from 1 to 1 over 8. Okay, so that's how those get replaced. Now we can integrate. The integral of e to the u is just e to the u. There's a negative there, so negative e to the u. So that would be negative e to the, plug in the upper one, subtract, actually going to be plus, and then plug in the lower one, e to the 1, which is just e. Okay. So probably people would write this like e minus e to the 1/8. Okay, let's do some more. Number 10. Okay, so you have the integral from 8 to 9 of x times the square root of x minus 8. Okay, so here, you have the square root of something, so that's a good choice. So what's inside is a good choice for the inner function. So u is x minus 8. Okay, take the derivative of both sides, and you get du equals dx. Okay, so you just have that part there. So you only have, I should do this in red. So this part is actually just right there. Okay, so you have this x right here that's a problem. But like we did before, if you solve for x, you get u plus 8. Okay, so this x gets replaced with a u plus 8. Okay, that x gets replaced with u plus 8. And this x minus 8 gets replaced with a u. So you have the square root of u, or let's write it as u. Well, let's write it as square root of u to keep everything the same. And then the dx gets replaced with the du. So we have that now. And now let's see, we can replace the limits as well. So these limits are in x. You're integrating with respect to x. So the upper limit is x equals 9. Lower limit is x equals 8. So u would be, okay, u is x minus 8. X is 9, so that's 9 minus 8, which is 1. And here u would be, wow, 8 minus 8 would be 0. Okay, so good. The limits of integration improved. Integrating from 0 to 1 is usually easier than integrating from 8 to 9. So that's good. Okay, now we'll distribute this square root of u in. And u times the square root of u is actually u to the 3/2. And then you have 8u to the 1/2 du, like that. Okay. Now it's time to integrate. So we raise this by 1 power to 5/2. When you take the derivative of 5/2, it's going to come down. So we'll counter that with a 2/5. And then here, raise that by 1 to 3/2. So when you differentiate, a 3/2 is going to come down. So we'll counter that with a 2/3. And that's going to go from 0 to 1. From u equals 0 to u equals 1. Okay, so put in a 1, and you're going to get 2/5 plus, you can putting 1 in here, you get 16/3. So those are 10. This is 1 to the 5/2, which is just 1. This is 1 to the 3/2, which is still just 1. Minus, and then plug in 0, you get 0 plus 0. So put 0 in for u, you get everything zeros out, so that's great. And if you take 2/5 and 16/3, you get 86/15.